Hello everyone and welcome to our lecture for week 8. Today we're going to cover two areas or remedies from criminal law. I'm going to do that through chapters 10 and 11. We're going to look at how fines could be implemented to achieve an optimal solution to an example, in particular double parking, and how imprisonment could also be used in relation to car thefts. Alright, let's get started with chapter 10 and using fines. Here our emphasis is not really on choosing a rule. We know the rule that we want to choose, which is fines in this case, but we want to design our system so that we can minimize the costs, in other ways, to maximize the net benefits, so to have an efficient design. So let's look at an example of double parking in a city called Econville. It has several million residents, and we'll assume that each one of these residents owns a car and that they occasionally double park. Okay, I will assume that the cost of double parking per incident is equal to $10. Now, the benefits from double parking, the benefits from double parking depend on the circumstances. So what you are double parking for. So if it's, for example, to get ice cream, then definitely the benefit is going to be less than $10 cost, or at least we'll assume that in our example. However, if it's for getting an urgently needed medicine, then we'll assume that the benefit is greater than the cost. And you can of course see that when that happens, the net benefits are going to be positive compared to the negative net benefits from getting the ice cream, and that makes the second possibility, second circumstance, is an efficient one compared to the first. Alright, let's assume also that there is 100,000 individuals in Econville, okay, and 100,000 per year, and that they obtain benefits from double parking that are greater than the $10 cost. So we'll assume that these 100,000 individuals have an efficient reason to double park. Okay, so this is an efficient outcome. So when we design our system, we're not really trying to minimize, to eliminate this outcome because it's efficient, but what we are trying to eliminate is the inefficient outcome. So double parking when people actually want to get an ice cream. Okay, that's the kind of behavior we want to stop. So ideally, there would be 100,000 double parking incidents in Econville each year. So these are the ones we just talked about. These are the ones involving benefits greater than 10 because they're efficient. So our system, our legal system, will not try to stop them. So this is very important. The legal system is not going to be designed to stop all double parking. That's not how we design our legal systems. What we are trying to do is to eliminate the inefficient behavior, i.e. when people double park to get ice cream, for example. Alright, so we will still allow for double parking, but only when the double parking is for an efficient reason, i.e. where the net benefits are positive. Okay, the benefits exceed the costs. Now, the council is going to try to design this system, and they're going to impose two things. Okay, or they have two decisions to make. First is the fine and how much they're going to fine someone who double parks, and the second thing is how much enforcement you're going to have of these fines. In other words, how many inspectors you'd hire to actually regulate the system, to monitor double parking and to issue the fines. All right. We'll also assume that the maximum fine that could be imposed is equal to the wealth of the double parking individual, and we'll assume that to be equal to $10,000. Of course, if it's greater than 10,000, then they can't actually pay it, so it won't have the effect required. That would take us to something different, which is like imprisonment, which we'll talk about in a minute under chapter 11. Okay, so these are the two decisions we have, and the analysis is on page 81, table 8. We're going to start by assuming that if we hire one inspector full-time for a year, all the costs associated with that are going to be $1 million. Okay, or sorry, that's actually 10 inspectors. So if you hire 10 inspectors full-time for 1 year, they'll cost you $1 million. That's the first option. Second option is to have only one inspector full-time, and that's 100,000. Or you can have one inspector part-time, so something like 3 months per year, so that would be only $1,000 per year. Alright, so we have these three options. So again, I'm just limiting the options so that we can look at the analysis and identify what would be the optimal design. So we are limiting the analysis to these three options: either 10 inspectors full-time, or one inspector full-time, or one inspector part-time. And as you can see, the probability of detection will vary depending on the number of inspectors you hire. If you have 10 hired full-time, we'll assume that that's enough to give you complete certainty that you will monitor the system and catch anyone who double parks. So certainty of actually detecting double parking is complete. It's 1. Okay? So the probability of detection is 1. And as you start going down, you reduce the cost by reducing the number of inspectors or their full-time employment. You'll find that there's a proportionality between the reduction in the cost of enforcement and the probability. So 1 million to 100,000 is the same ratio as 1 to 0.1. Okay, so the idea is that you are reducing the probability proportionally to the enforcement of costs. Then we're going to impose a fine, and that fine is going to be imposed in order for us to get an expected fine. So in order for us to be able to look at where we can deter people from double parking or not, we want to set the expected fine equal to the cost faced by each individual. We saw that the benefit relative to the cost decides whether someone is going to double park or not, or whether it is something efficient for them to do. So that's why we want to set the expected fine equal to what we assume to be the cost per individual, which is $10. Now once we have decided the expected fine, we can go back and check what kind of fine we have to have in order for us to get that expected fine. Remember, the expected fine is nothing more than the value in the second column, which is the probability, times the fine itself. That's the fine that will actually get the double parking person or individual to pay. Okay, so that's what's imposed by law. So if you look at the first row in relation to the probability of 1, you'll find that we have a fine of 10, because 10 times 1 is equal to 10. Drop down to the next one, it's 100 times 0.1, which is again going to give us 10, and the last one is going to be the 10,000 times 0.001 and gives us 10 as well. Now remember, the 10,000 comes from our assumption that that's the maximum fine we can impose, which is equal to the wealth of the individual, which is equal by assumption again to 10,000. All right. So which one of these are you going to choose? So you can see that the expected fine is all going to be 10, but of course the council is going to choose the costs of the option that minimizes the costs, and hence they would choose to spend only $1,000 hiring someone only part-time, which will give them the same expected fine, and from there, of course, as far as they're concerned, the same benefit to them from catching these double parking individuals. Okay. Now there's a law and economics scholar by the name of Gary S. Becker, and Gary of course comes from the Chicago school, and he said the efficient system of law enforcement is the one in which the fine is as large as possible, equal to the wealth of the individual whose behavior is being controlled. All right. But the question, of course, if, okay, so when the fine is as high as the wealth, $10,000, is it still reasonable to assume that people will still be risk neutral? Okay, when you are saying that I'm going to impose this fine, as we saw here, because we chose to go with the third option. So now you're saying I'm going to impose a fine of $10,000 on anyone who double parks. So the maximum possible fine, which of course reduces the costs faced by the council. Okay. Now the question is, if people see that are they going to still be risk neutral? Is it that all they care about is going to be the expected outcome, the expected value of the fine? So we can now change our assumption of risk neutrality to risk aversion, and in order for us to model this risk aversion, we're going to add a risk premium. So the idea, for example, is that if we are talking about a probability of deterrence of 0.1 and a fine of 100, the expected fine is going to be 10. For risk neutral person, they're going to look at it and say, okay, I would double park if the benefit is greater than $10. That's all they look at, the expected fine. However, a risk averse person will look at the expected fine plus something else which represents the extra cost to them because they are risk averse, which is what we call the risk premium. If we assume it's equal to 1, then the risk averse person will double park only if the benefit that they get from doing so is greater than $11, not $10. You see, so they would double park less because they expect the benefit to be much higher in order for them to break the law that way. Okay. All right. So if we, for example, now lower the fine to something like $90, okay, so multiply that again with the detection probability of 0.1 gives you $9. Then we add on top of that the risk premium, then that will still give us the expected fine that we want, which is equal to 10. And that's what we see on page 85. And here we can see how a risk averse person would look at the situation. So again, the probabilities of detection are the same as before. In the middle here, in the fifth column, we again see the expected fine equal to 10 because that's what we want, because that's what the cost is equal to. And you'll find that when we impose a fine of $10 times the probability, it will give us an expected fine, but then we have to add a risk premium that increases by the increase in the fine. Okay. So you'll find that the total always going to be equal to 10. However, the risk-bearing costs now, which is the sixth column, and it says there in our note C, it says equals column 4 times 100,000, because that's the number of people that we said are going to double park, and would be subject to this risk. So that is going to then be column 4, which is the risk premium, times the number of people that are going to commit this double parking. So it will give you the number or the costs of risk bearing. So the risk bearing cost is something that only a risk averse person is going to see. Okay. Then you have the enforcement costs, and these enforcement costs are just as before when you have either 10 full-time inspectors or 1 full-time inspector or 1 part-time inspector, and then you add them up and you will get a total cost. The key thing here to remember is that the risk-bearing costs are increasing in probability of detection. So as you reduce the probability of detection, the inversely proportional basically, as you reduce the probability of detection, those risk-bearing costs will increase. Okay. However, the enforcement cost will go down as you reduce the probability of detection, because you don't want to detect many, so the cost that you'd pay to get that probability become less. So these two things are going in different directions. So when you add them up, you'll find something what we call a smiley face, or something like a bathtub curve. Okay, so you'll find that it starts with high costs, then it drops down to 200,000, and then it goes up again to 801. So what we of course are trying to do here is to minimize these costs. Okay, so that would mean that we will choose the probability of detection in the middle, which is equal to 0.1, and now instead of having a part-time inspector, we're going to hire an inspector full-time. Alright, so again here in the risk-averse example, given the probability of detection, it is always possible to set the level of the fine so that the sum of the expected fine and risk premium equals the harm caused by an individual's harmful activity, i.e. the double parking. And also look at the footnote 55 on page 86 that explains this in some more detail. And it says that note there is a trade-off again between the minimizing the cost of enforcement and the cost of bearing the risk. This is what we talked about in relation to the smiley face. So that's one of them is going up and the other is going down. The efficient outcome is where the sum is minimized, and now the optimal outcome, as we said, is to choose a probability of detection of 0.1 and a fine of $90. The general rule we can take out from this is that if an individual if individuals are risk averse, then the efficient system of law enforcement is one in which the fine generally is not as large as possible. So instead of a $10,000 fine as we saw with the risk neutral people, now because they are risk averse we only need $90 because they are already risk averse. Okay, it's not as large as possible, and the probability of detection generally is not as low as it would be if individuals were risk neutral. So you would have an increase in the probability of detection, the optimal outcome, and a huge decrease actually in fines. Alright. And then there's something about relaxation of some of the assumptions that we've made in this chapter. So we're talking here about some of the assumptions we talked about and how they were relaxed. It's just a minor point that we don't have to really worry too much about. So I think I'm going to just leave it for you to look at on pages 89 and 90. Alright. Let's then continue with the second type of remedy or intervention under criminal law, and that is imprisonment. So now we're not going to look at fines, we're going to look at imprisonment. So we're going to assume that imprisonment is the only sanction, although in reality, of course, you usually have combinations of these, such as under corporation law acts, or such as consumer protection acts, and so on. So our example now is going to be about an individual that steals an automobile. Okay, and there are two decisions that the state will have to make. The first is how long the jail term should be and how much to spend on catching this individual that steals the car. And what we will find is that the decisions depend on the relationship between something that comes as this utility. We're not going to delve much into how we define how we measure this utility, but it's just the ability, if you can think of it as the suffering that someone gets from being in jail. And we're going to assume that this is perfectly measurable and we have all the information available, so we can look at how we can minimize the costs. Alright, so to start with, we're going to assume that there's a proportionality between this utility and the length of the jail sentence. So let's look at this table here. We're going to assume first of all that we're going to have 10 thieves, so 10 thieves in total, and the cost to the state of putting them in prison if they are caught is $75,000 per year. So this is the table that we have on page 93, and we're going to assume at the end of the chapter you'll find that there's a link then between these assumptions of this utility, proportionality with the length of the jail sentence, and the idea of risk inclination, whether you are a person that's risk neutral or averse or risk seeking. The first table here is actually a reflection of someone who's risk neutral. And why is that? Because as you double, for example, the number of years of the imprisonment sentence, you simply also double the suffering or this utility that they have from being in jail, which means that if, for example, we assume that there's 1 year and we know that the state wants to impose this efficient outcome in their minds, is that the best thing to do is to have 1 year jail sentence, and that would impose a suffering of 100 on the thief. But if you impose 2 years, then you simply double that, so it becomes 200, and 5 it will be 500. So in order for us to have what the state wants, we want to have the expected utility to be always equal to 100. So the probability of detection now will vary such that when you multiply that by the units of this utility, you always get this 100. Okay. Now these probabilities of detection will also affect what? Affect the enforcement costs. As before, we would say that we'll have a $1 million if we want full certainty that we'll catch all of these 10 thieves, or it is actually going to halve if the probability halves, and so on and so forth. And there's something at the end in the last column, column 6, that talks about imprisonment costs, and these are nothing more than getting the total costs to the state from actually imprisoning all the 10 thieves, given the probabilities of them being caught. So you find, as the explanation in note D says, the last column is simply the 10 people, the 10 thieves, times column 3, which is the probability of detecting them, because the state will not incur these costs until unless these thieves are caught. So those are the probabilities of catching them, and then times the imprisonment sentence, because our assumption as to costs per thief are also per year. So we said 75,000 per year, so if 2 years, then it's going to double, and so on and so forth. So we have to multiply number of persons, which is 10, times the probability, times the number of years, and then times $75,000 per year. That gives us the total number, the total amount that's going to be imposed on the state in relation to imprisonment costs. And as you can see, that it's always going to be equal to 750,000, which simplifies finding the optimal solution, because now we know that the only thing that makes a difference is reduction of enforcement costs. So the most efficient outcome would be to have the same imprisonment, would be able to have the same expected disutility to the thief, but with the lowest possible enforcement costs. So the highlighted third column would be our efficient outcome in this case. And the general rule is simply, if the disutility for imprisonment is proportional to the length of time in jail, the efficient system of law enforcement involves using relatively high sentences and correspondingly low probabilities of detection. So something very similar to what we saw in our analysis of the fine, design the fine system in chapter 10. Alright, now let's change our assumption and say that the disutility in fact is going to rise more than proportionally, meaning what? So if you look at the first two columns now in table 11 on page 95, you'll find that the imprisonment sentence at the beginning is going to be 1 year for 100 disutility units, but if it's doubled, the disutility is going to triple. So it jumps more than the number of years, which of course is something that reflects risk aversion. So if it's 5 years now, the disutility jumps to 1500 units. But we also always want to have the expected disutility equal to 100. So now we have the probabilities as shown here and the corresponding proportional enforcement costs, and the imprisonment costs are always 750,000 as before. And again, we find that we want to reduce the enforcement costs, which means that we'll still go to the longest possible imprisonment sentence. So the general rule, if the disutility for imprisonment rises more than proportionally with the length of time in jail, the efficient system of law enforcement again involves using high sentences and low probability of detection. What about then if we say that the disutility rises less than proportionally? Now this is where you find someone who's risk preferring. Meaning what? Meaning they're suffering from this sentence that you're going to impose on them is going to diminish. It would have diminishing sort of marginal returns, what we call, or if you think of it as saturation. Okay, so after 1 year they have 100 units of suffering. If you put them there for 2 years, the suffering is not going to double. It's going to be like 150 units. And if you put them there for 5 years, it's going to be only 194 units. Okay, so looking at that and expecting our utility to always be 100, now we know what our probabilities of detection are going to be, and from that we can find the enforcement costs as before, proportional to the probability of detection. And our imprisonment costs now are going to be a little bit different, but they're always going to be equal to what we saw before. So it's the number of thieves, the 10 people, times the probabilities, times the years, and times the $75,000 per year. That would give you the figures in the sixth column, and the last column is simply a sum, an algebraic sum of the two columns 5 and 6. And again we see a smiley face. So we start with a large value, it drops down and goes up again, and the reason for that is that our enforcement costs are going down in relation to the increase in the length of the imprisonment sentence, and the imprisonment costs are going to be increasing with the increase in that sentence. So you'll find now that the efficient outcome that reduces the total costs is in fact not the maximum sentence, but something like a 2-year sentence that reduces or minimizes or optimizes the costs. The general rule is raising the imprisonment sentence and lowering the probability of detection has conflicting effects. That's what we talked about with this bathtub or smiley face change in the total costs on the costs of enforcement and the cost of imprisonment. The last point we talk about in this chapter is a comparison between fines and imprisonment. Of course, fines are less expensive and should be employed first, but it also, of course, depends also on the type of crimes that we're talking about and the societal expectations of punishment in relation to these crimes. Alright, so we'll leave that there then, and I'll be talking to you again soon.